So I think I'll go ahead and welcome everybody to this week's soil seminar. Reminder that we are recording the seminar. And today's speaker is Dr. Jason Ackerman. He is an assistant professor at Purdue University. As a soils extension specialist, he has duties in both extension and research. His research and extension program focuses on applications of soil science to improve the capability of soils to support agricultural production and provide ecosystem services. And with that, I will turn this over to Dr. Ackerman. He's going to present today on pedology, pedometrics, and soil health, leveraging novel data streams to enable soil conservation.
Thanks, Matthew. Let me get my slides up real quick. Great. So, yeah, I'm excited to be here today to talk to you about sort of some of the research my lab is doing. I feel like I need to apologize a bit for this title. Someone once told me that every good title needs to have a colon, and it's just so you know that that talk's going to be full of crap. So this is me trying to sort of stretch my research program a bit into the sort of soil health world. So I'm a pedologist and a soil physicist kind of by training. And a lot of the work that my laboratory does sort of focuses on new measurement systems for soils, how do we collect better or more useful soil data at a lower cost point, and then how do we apply that data to sort of maybe some technical challenges that we see in the soil science world. So recently we've been trying to take some of these tools and apply them in the context of soil health inventory, either mapping soil health as a current state or a potential state at various spatial scales. So let me see if I can, there we go. So I might have subtitled this talk, Soil Health, a Pedologist's Existential Crisis. And I think about this from a pedologist's point of view. Soil health is sort of this maybe a nagging little bit of a curiosity, right? We know that soils evolve and change in time, and soil health is just a singular snapshot of what a soil's particular properties or condition is at one point in time. And so I think as a pedologist, I often thinking about questions related to soil health, although I might not be using the same terminology as some of the soil health people. But a lot of the questions that sort of keep me up at night as a scientist are things related to inventory of soil health, specifically how do we measure or quantify soil health? In human systems, we have a pretty good analog, right? We can measure somebody's fitness. We can measure their VO2 max as a measure of how respiratorily efficient they are. We can measure their body mass index to see how much, if they're overweight or underweight. We don't really necessarily have those same analogs in soils, and I think there's maybe some spirited debate out there whether or not we should. Given that soils have an inherent capability or condition that is defined by sort of their pedogenic history. So we're going to briefly touch on some of the stuff we do in my lab to try to answer some of these questions specifically related to measurements around soil health, inventorying soil health, mapping it at a couple different spatial scales. And then I want to sort of leave off with sort of those last two questions of can all soils be equally healthy, and how do we know how healthy an individual soil could be? Some of the new work we're doing that's a little bit more forward thinking, I think. So without further ado, we're going to get into some of the work my lab does to rapidly measure and map soil health. And now I'm kind of being a little cheeky here in the fact that we're really not talking about soil health indicators in terms of like phospholipid, fatty acids. We're talking about things we can actually quantify maybe more consistently, and specifically thinking about soil carbon. So we'll talk a lot about soil carbon in my talk today. But so just a quick overview of one of the main tools we use in our laboratory, which is visible near-infrared spectroscopy. And for those of you who aren't familiar with this technique, it's an optical technique where we scan a soil and measure its reflectance as a function of wavelength. So an individual soil might have a wavelength or a spectra, looking like the upper right-hand graph here. And you see all the peaks and valleys I explain this to my students oftentimes as sort of the soil's fingerprint. And we can convert those spectral reflectances. If we have a sufficiently large data set of soils with measured reflectances and laboratory data, we can build models to predict the soil properties based off of the reflectance characteristics. So this is a model predicting the clay content of soils. This is about 2,000 soils with measured reflectances, and we can predict the clay content. In this model, it's kind of poor. We're looking at, not poor, it's actually quite good, RMSE of 9.8 grams per kilogram, which is around 10%. For context, we think about the typical RMSE of a hydrometer method of being around 7 or 8%, depending on the operator. So with a lot of these spectral techniques, we can get pretty close to laboratory standards. The issue is you still have to take a soil, sample it, dry it, grind it, and process it in the laboratory to get any useful information out of it. So what we've focused on maybe over the last 5 or 6 years throughout my postdoc and now here at Purdue is taking this laboratory technique and moving it into the field. So we built a in situ visible near infrared probe. And you can sort of see a cartoon of that on the left-hand side. So it's a stainless steel cylinder that is sort of inserted into the ground using a hydraulic probe, a Giddings machine. And there's a small window. You can see a sort of clear circular pattern in the center of that probe. And inside of that is a fiber optic that actually collects the visible near infrared signal. And so this technique has really enabled us to go out in the field and sort of skip the whole step of collecting a soil sample, processing it, and drying it and doing all the manual labor there. We just need to take the machine out to the field, push it in the ground, and we can collect soils data in situ without having to actually take soils back to the lab. So this opens up a whole realm of rapid soil inventory where now we just need to go out and poke some holes and we have all the data we need to start building soil maps or doing soil inventory. So the way this works in practice is we can correlate measured soil spectra with a laboratory-based library and build prediction models to sort of predict at really high spatial resolutions or depth resolutions changes in soil properties. So in this graph, we're showing a depth profile of soil clay content with the the white dots showing the in situ data. Black dots are showing data collected on those same soils in the dried ground or laboratory condition. And the blue bars are showing places where we actually collected a soil sample and ran pipettes or laboratory standards. So with this data, we can get really, really high depth resolution profiles of soil properties. And as a pedologist, this is really great. You can start thinking about how soils change in space, both laterally and vertically. For example, for context, this is a paleostyle that we've sampled, and you see the big spike in clay content around 60 centimeters, denoting the BT horizon. And this is one of those really unique sort of bimodal soils we see a lot of times in the Texas clay pan areas. So really neat tool for getting lots of soil data. And we can start then taking this to other places and sort of verifying its properties or its capabilities. So the two panels we're showing here show data from Iowa, Illinois, South Dakota, and Texas, where we took the same spectrometer, same laboratory models and everything, and collected in situ profiles, and then did a sort of accuracy test of the in situ VisIR model performance. So on the x-axis here is looking at either the measured clay content on the left or the measured soil organic carbon content on the right, versus the VisIR predictions on the vertical axes. And in both cases, we get pretty solid and repeatable measurements. Our RMSEs for clay content in this case are below 6%, so that's about as accurate as you could get with a pipette. And our concordance correlations are around 0.8, so very high levels of concordance correlations. So in both of these cases, we have a tool that gives pretty accurate and precise measurements without the need for going out and doing a lot of excess soil sampling, soil processing. I'll also point out maybe the most important result here is the bias of all of these data are essentially zero. So what that means is if we take this instrument to a field and we make a measurement with it and then subsequently build a model, we won't have any propagation of those biases or errors into subsequent models. So oftentimes an instrument that's maybe less accurate or precise, provided it's unbiased, is maybe more valuable. And in this case, we have a tool that seems to be accurate, precise, and unbiased. So we're pleased to see this result, and it looks like we have a viable tool moving forward. So that's sort of the first piece of how do we map or how do we measure soil condition in place. So we've got a tool that can measure soil organic carbon contents pretty accurately at a pretty low cost. Sort of the next question we want to address is how do we take those data and actually build useful maps or inventories with them, right? We would expect that in a field, we're going to see some variation in soil organic carbon stocks or soil health indicators if we want to be a bit more broad. So we're going to show you a sort of quick proof of concept of taking that penetrometer-based system or the VisIR-based system and applying it to high-resolution digital soil mapping. So for those of you who aren't familiar with digital soil mapping, I know Bradley's group does a lot of this, but essentially it's a way of building high-resolution models or geospatial models of variabilities in soil properties. So in this case, we've outlined kind of a really crude schematic of what the digital soil mapping project would look like. So first, we're going to identify some sort of data need or reason for building that map. In this case, we're going to think about we want to quantify soil organic carbon concentration variability across the field as part of a broader soil health inventory. And then once we know what our target variables are, we need to collect some soils data and some corresponding environmental covariates. These are things that sort of describe the pedologic or adaptive environment of that field. And then we correlate those environmental conditions to measured soils data through some sort of empirical model and then generate a map. So what we're going to focus on today is sort of one of the easy ways we can expedite this digital soil mapping paradigm is by changing up the soils data we're using. So instead of collecting actual soil samples for model calibration, we'll be using visible near-infrared spectra. And we'll also do some pretty neat stuff with our choice of models. Okay. Hey, oh man. So to set the scene, I missed a slide here somewhere. So our target field is a 40-acre corn and soybean field in Nebraska. And this is sort of a schematic of that field. We have sort of two 40-acre sections here shown in this sort of relief map. And each one of those arrows is a place where we've collected a soil core. So we took those cores back to the lab. We cut them sort of lengthwise down the profile, and then every 2 centimeters along that soil profile, we collected a visible near-infrared spectra. And like we showed earlier, we can use those spectra for all sorts of predictions. One of those being soil organic carbon content predictions. So the panel here on the left is showing a profile of organic carbon stocks with this open circles representing the visible near-infrared spectra and the red circles representing places where we have laboratory standards to correlate with them. And we see a pretty good relationship between our visible near-infrared predictions and our predicted or our measured soil organic carbon concentrations. So now we have this really high resolution profile for every location in that field. So we have, I think, something like 70 points where we've gone out and collected a core. And now we have, for each one of those locations, we have a high, 2 centimeter resolution profile of the soil organic carbon stocks. And so we took these profile data, and I'm not going to jump too much into the details of the modeling routine we did here. It's a system called generalized additive mixed models, and it's been used in a couple places for digital soil mapping. specifically Laura Poggio out of, I guess, Scotland has been doing a lot of mapping there of their carbon stocks using this routine. And if you're familiar with sort of splines, the GAMs use a sort of three-dimensional tensor structure, which is kind of like equivalent to a three-dimensional spline to predict soil properties. And what's really neat about that is it actually generates a true 3D model of the soil landscape. Typically, in a lot of digital soil mapping applications, you generate a unique map for each depth slice. So you might say, let's look at the 0 to 5 centimeter carbon concentrations, and let's generate one map for that depth slice. Well, what the JAMs allow us to do is generate the model in sort of one shot. So we're generating all depth layers and all locations in the field in one single shot. The other nice thing about this tool is it allows us to integrate some environmental covariate data into those maps. So in this case, we're using LiDAR-derived terrain attributes, some electrical conductivity measurements, and as well as some satellite imagery. And we sort of jump it all into the GAM blender, and comes a really nice three-dimensional map of the soil organic carbon concentrations. So the colors here indicate the concentrations of soil organic carbon in our sort of three-dimensional model. We've kind of stretched it and twisted it a little bit. And we've also expanded the vertical axis here. So the vertical axis goes from 0 to 1 meters in depth. And then again, this is a sort of 2 40-acre sections of a field, with the darker colors representing areas of high carbon concentrations and the lighter areas representing lower carbon concentrations. So there's a couple neat patterns we notice in these models. Firstly, we do see, as we would expect, a strong sort of grading of carbon concentrations away from the surface. So our highest concentrations are located at the surface, the lowest concentrations sort of in the subsurface. We also see concentrations of carbon in the sort of depressional locations in the landscape. So if you look at the map here, or the model here on the surface, you see this sort of section of darker color that runs roughly from southwest up to the sort of center of the top of the image, sort of a dark band of carbon. And that's actually a relic stream channel where we have overfill kind of washing in and having slightly wetter soils with higher concentrations of carbon. And when we investigate or interrogate the accuracy of these models, we see that they're pretty good. We're reaching a RMSE of around 0.3%, which is equivalent to the accuracy of our Vision IR models. So we're not really seeing any model accuracy loss in the sort of spatial interpolation side of things. It looks like most of our inaccuracies might be derived from the stock predictions or the concentration predictions themselves from the Vision IR. So we have a pretty accurate model, but we also, the nice thing about this routine is it allows us to look at the uncertainty of those models. So in addition to predicting the average or median concentration of carbon stocks, we can also look at a prediction interval or confidence interval around those predictions. So here we're looking at sort of 2 depth slices through that field, one at 0 centimeters and one at 30 centimeters. And on the left-hand side, we're looking at the median concentration, or the 50th percentile of all of those model runs. And on the right-hand side, we're looking at the 95% prediction interval, sort of binning those carbon stocks. So now we can also not only look at where we believe the carbon is in the field, but where our knowledge about that carbon distribution may or may not be accurate, or might be more or less inaccurate. So one of the things to notice is because we are using a sort of interpolant or tensor type model, we do see around the edges of our models high levels of model uncertainty. So I'll draw your attention to the 0 centimeter depth slice of the prediction intervals. And in the southeast corner and then the southwest corner, we see these high concentrations of prediction inaccuracy or large prediction intervals. So this is telling us that we do see some level of inaccuracy or sensitivity in the model, I guess, around the borders where a model is unsupported by external data. So one of the nice things about this is it allows us to say and identify places in the model where we not only might be suspicious of those model outputs. For example, in the median concentrations, we see high carbon concentrations in the southeast corner, around 4%, which is quite high compared to the rest of the model, which might be an error due to the tensor structure. And correspondingly, we see that same increase in model uncertainty. So it gives us a sort of way of evaluating not only the accuracy of the models, but their believability, if you will. So, one of the nice things about this tool is it allows us to couple rapid measurements of soil carbon concentrations or other soil health indicators. We're currently working on some other spectral related soil health indicators. I don't have that data here to show you yet. But it allows us to build 3D models of soil health or soil carbon concentrations more specifically at high levels of accuracy within a field. So we've got a tool that lets us collect lots of soils information, and then a set of tools that let us use that information for sort of three-dimensional or geostatistical interpolance of that data, and understanding the spatial patterns or spatial variability in those properties. And so far, this seems to work really well at just a single field scale. So the next thing I want to sort of talk about is how we can maybe take some of these tools and apply them at larger extents. So instead of focusing on an 80-acre part of Nebraska, what do we do when we want to take some of these tools and scale them up to, say, whole watersheds or states or even sort of continents, right? So the first thing I think we need to discuss is the fact that when it comes to soil health or mapping dynamic soil properties, whatever we want to call these attributes, the covariate choice is really important. And specifically, those covariates need to describe to some extent the management or the management history of those soils. If you talk to anyone in the soil health world, right, they'll say that, putting on cover crops and adopting no-till is going to improve your soil's health. Well, if we're trying to map that, we then need to also know where producers or land managers have adopted those conservation practices. So a lot of states, Indiana in particular, have adopted some sort of conservation assessment program where they do some manual inventories of the different management practices across a field. So this might be a useful covariate when thinking about mapping or predicting soil health at larger scale. So in Indiana, they run a manual survey of every county twice a year now, and they measure things like the amount of residue cover that they see on the ground, the proportion of different tillage practices, and the presence of absence of cover crops, and then what crops have been planted in that watershed. The challenge with all these data is that in most cases, they're only available at pretty coarse scales. So in Indiana, this data is really only available at the county scale. So if we're trying to map, say, within a watershed, the effect of tillage practices on soil health conditions, this data is really of no use to us. So we need some other tools to map or monitor these conservation practices. So this is a project my first PhD student adopted, and I think it's been really successful, but it is, I'm gonna warn you, not super soil sciencey and also kind of a little weird. So I said to Jeff, my student, I said, we need to know where people are planting cover crops, we need to know where they're tilling, and it needs to be an accurate enough data set that we can then take it and build watershed level maps. And Jeff and my idea was to build our own soil science Google Street View car. So Jeff took and purchased a couple GoPro cameras. We mounted them to the roof rack of a car, and we drove around our target watershed collecting images of the soil landscape. So you can see a picture of our very scientific looking set of cameras mounted to the car here, and then what his sort of images look like. So when Jeff will go out, drive around his target area, download the images, and then we have some programs that help him classify those data and capture identify maybe what the sort of tillage practices, previous crop, crop residue cover would be in those fields. So our target watershed for this sort of pilot study was the Big Pine Creek watershed in Indiana. It's a really typical I-state sort of watershed, 90% corn and soybeans, a little, maybe about 50% no-till, and the occasional cover crop here or there. But it's a pretty standard, bog standard Indiana watershed. So Jeff drove his car sort of along the blue route, as you see there, sort of covering a large extent of that watershed. And I will say this route is not random. This is designed to target places where we know specific practices are being implemented, so we get a good, relatively stratified view of the different types of practices in the watershed. So Jeff's, I dropped an M there. That should say methodology, not ethodology. So in Jeff's process, he drives around, and the car is enabled with a GPS, and the cameras have GPS on them. And so what that sort of looks like in practice is on the right here is a Sentinel-2 satellite image of the fields, and the dots represent the left and right cameras respectively as he drives down the road. And the road here is in white. It's been cropped out of those satellite images. So at each one of those points, Jeff knows sort of the field of view of the cameras, and then he will he has an automated script that kind of shifts those points out into the field. So we kind of have an idea roughly of where the image that's collected from the car cameras is pointing to in the field. And then we can geo-reference those images to a satellite image, which then Jeff correlates to his manually annotated images. So he might take one of these images and say, and it's hard to see on this screen, but he'll look at that image and say, that looks like soybean residue. That's about 20, maybe 45% residue cover. And it looks like they ran a strip till machine over it. I'm sort of wildly guessing at that. Jeff has done thousands of these. He's much better than I am. But then he takes that annotated data, compares it to the satellite imagery, and builds some remote sensing classifiers to then predict out where those different management properties are in the field. And so that allows us to start building really high resolution maps of agricultural management practices. So here's a map based off of a Sentinel image predicting the types of tillage practices across the field, or across the watershed, excuse me. So he has sort of two main tillage systems we see in the field, in the watershed: mulch till and no-till. So that's a good sign for the conservationists. Roughly, I think it's 70% of this watershed is in no-till. And he also denotes areas where either there is no tillage due to the presence of pasture or CRP land, and then also places where they have yet to till because the crop is still standing. So we have a really high resolution, it's a 30-meter resolution raster that describes the tillage systems in that watershed. Additionally, we could start looking at percent residue cover. So he's broken up that same data into the percentage residue cover that describes where different residues are in the field or across that watershed, and we can start locating areas of high concentration of residue cover or areas of low concentration of residue cover. And we can also use that same data to predict where there are cover crops planted in and out of those fields. So I'm pretty excited about seeing these results. We're just starting to get the first returns back from these data. But it's giving us a really in-depth view of where different practices are in this watershed. And our sort of next step, which we haven't really gotten to yet, is to take that data and start using it to build some soil maps, right? Taking it and using it as a covariate to predict soil carbon concentrations or various soil health indicators across the field. The other thing that Jeff's doing that's really exciting is he's taking those images and putting them through a convolutional neural network, which is the sort of same stuff that Google and Facebook use for image recognition. And he's building an image classification library for this system. So our hope is over the next couple of years, we'll have enough data in the system where you just drive the car out and then download the data, and the computer does all the heavy lifting, and then we get really high resolution maps of what's happening on our farm fields. So I'm really excited to see where this project takes us. Sort of the next step, as a pedologist, I'm really curious about how we can utilize this as a covariate and digital soil mapping techniques, but also have colleagues who are interested in using it to maybe identify locations where we might want to try to intervene with farmers to promote cover crops or reduce tillage systems. So really excited to see how that process goes. So the last project I want to talk to you about is one related to soil health benchmarks. Soil health indicators or anything describing soil health needs a reference state or a benchmark to compare it to, right? I used the analog earlier of talking about body mass index, right? I can calculate my body mass index and compare it to other people to determine whether I'm over or underweight. We don't necessarily have the same data for soil health, right? If we're using an indicator like soil organic carbon, we don't know specifically what that organic carbon stock should be for any given soil. And that has really big implications for land managers and farmers, right? If they're interested in identifying or targeting a soil health outcome, say, I want to increase the carbon on my field to XYZ number, they don't know if that number is realistic or is representative of the soils. And certainly we know that things like soil organic carbon concentrations change just due to pedogenic factors. So we're looking at building ways of identifying or building virtual benchmarks. So the hypothesis we're working off of, and I should say I'm working on this with another colleague in my department, David Camerano, who's a really good ag systems modeler. So I'm going to show you some modeling stuff that I had no part in. I just had the input on the soil side. So our sort of working hypothesis here is can we simulate indicator benchmarks that should be what a benchmark should be under a given management regime or a set of soil properties. So our approach is to simulate soil organic carbon stock evolution on benchmark soils across our study area. And then we quantify the relationships between the soil organic carbon stock evolution and static or mappable soil properties. So we have a really good database of what those soil properties are out of the Surgo database, and we want to try to link our measured or modeled benchmarks to that existing soil database. So that's sort of the last step, is to use the relationships we quantify in the study to predict benchmarks for unstudied soils. So our modeling approach, David is big onto the DSAT world. So he ran a couple DSAT and Century models. So Century is a soil carbon biogeochemical model that sort of maps or predicts soil carbon evolution. And we sort of based everything here off of a benchmark corn and soybean rotation. And one of the things we're interested in later dates is taking this and changing that management regime. What happens if we add hay into the system, and so on and so forth. So we simulated weather and soil organic carbon stock evolution for a 100-year time frame. And essentially everything is the same for every model simulation we did, except for the soils data. So we picked 120 soil components from our target area, which is Major Land Resource Area 111. And we changed the soil parameters based off of Surgo data for each one of those components. So we have 120 soils that describe the range in variability of soil properties across our target study area. And we simulated the soil carbon stock evolution for each one of those soil profiles using the same set of weather data and the same set of agronomic data. And so we get a sort of 100-year trajectory of what would happen to the soil organic carbon stocks in each one of those fields. And so what we're really interested in is can we map or quantify some of the properties of how these simulated carbon stocks change. So specifically, we're interested in sort of what we're defining as two parameters. The asymptotic soil organic carbon stock, which we're calling SOC max. So we see as in this graph, as the simulation advances, the soil organic carbon stocks deplete and they reached some asymptotic value here, which we'll call sort of the equilibrium or max carbon stock. The other thing we're interested in is what's the steepest pitch of this line, or how fast do those stocks change under their most vulnerable conditions. And this gives us an indication of how quickly a soil might respond to management changes, or how much that soil carbon stock could change at any given time. So we took David's 120 simulations and we fitted a set of logistic curves to each one of those. And that allows us to sort of parametrically define that maximum slope and the asymptote from those sort of logistic curves. So now we have, for each of those 120 soil profiles, or soil series, I guess, we have the asymptotic carbon stock and then the slope parameter. And we're interested in figuring out ways of estimating those parameters based off of static soil properties. So we adopted a partial least squares modeling approach where we predicted each of those parameters, the slope and the asymptote, from sort of static soil properties. So in this case, we're looking at the slope parameter as it's modeled from static soil properties. Our R-squareds are around 0.4, which is not great. Sorry, 0.6. I don't know where that 0.4 came from. And then more importantly, though, we're interested in what soil properties from the DSAT parameterization files are driving those parameters. So on the table on the right is the top 10 PLS coefficients for those models. And parameters listed here relate to mostly to the water retention characteristics of that soil. So the 15 bar water content at various depths, the soil drainage rate, and then the bulk density all sort of integrate into this model in various ways. So one of the things that we sort of are picking up on is the vulnerability of the soil carbon stocks that we're simulating here is related to water retention characteristics, specifically things that we can measure around the water retention curve. So it seems that this would sort of follow the hypothesis we have in most of pedology, that wetter systems tend to stabilize carbon more quickly and at a higher level. So we can do the same thing for the equilibrium stocks. And this is showing the performance of those PLS models. Again, we're at around 50% with our R-squared. So these models aren't great, but they're reasonable for, I think, what we're asking them to do. And again, looking at the parameters in these models, they all again relate to things related to the soil's conditions. So the soil's drainage rate, its water retention characteristics. Interestingly, CEC crops up in this model pretty high up here. So the surface CEC kind of is apparently related to the maximum carbon stock at some point. Not sure what's going on with that. David's sort of digging into the nuts and bolts and Century to try to figure out why that would be the case. So ultimately, what's the point of all of this, right? How can we leverage this data in a useful way? And really what we were interested in is, can we take these data and use them to map ideas or parameters around soil health related to benchmarking these soils. So the two maps I'm showing you here are about a 40 square mile region of central Indiana, and they're colorized to the predicted logistic regression parameters from our PLS models. So we have a model that defines the relationship between static soil properties and their soil carbon stock evolution in our simulations. And we could take that model and apply it to every soil in our study domain. So these soils weren't necessarily part of our simulation. These were just predicted from those PLS models. And the neat thing here is we can start looking at parts of the landscape that have vulnerable or high carbon stocks. So the panel on the left is showing the curve of that logistics parameter. So the red areas or the pink areas are places where that curve is negative. So these would be places where under our given management scenario, those soils would be losing carbon. Blue areas would be places where we would see accumulation of carbon under that given management scenario. And then anything in white is either statistically not significant from 0, or that data is missing because it's a urban component or water in the Survey data set. So we can see that we've got large areas of sort of potentially vulnerable carbon stocks in this landscape. All of the peach are places where under our reference scenario, the soils would be losing carbon. And then all of the light blue that you see are places where we could potentially be gaining carbon. So from a management perspective, those would be places where we would maybe want to promote carbon sequestration or carbon loss mitigation from a conservation perspective. The panel on the right is showing our equilibrium stocks. So how much carbon is stored in kilograms per hectare on those soils at any given point in the landscape. So this gives us an idea of being able to say, okay, on this field, under this given management scenario, we could expect to store this amount of carbon. So it gives us sort of a way of detailing or identifying which carbon stocks or which soils are high stocks potentially for carbon sequestration. So I think with that, I'm about out of time. I would welcome any questions from folks. I know it's kind of a whirlwind. I kind of just threw everything in the kitchen sink.
Jason, thank you very much. There's a lot of interesting stuff that you're doing for sure. I especially like the GoPro cameras. So I think Jerry Miller has a couple of comments for you, if you don't mind.
Yeah. Hello?
Dr. Miller? Maybe you're muted.
Sorry about that. I couldn't get it unmuted, and I learned how to unmute this thing.
Fair enough.
Hi, Jason. Jerry Miller, retired pedologist on the faculty at Iowa State, now a couple hundred miles north of you in Grand Rapids, Michigan. So great.
Oh, I grew up in Grand Haven.
Oh, well, there you go. Home country for you. I didn't grow up here, but I'm here. And I just add, I'm not related to Bradley. Unfortunately, he would be a great son for me, but I'm not. But two comments, not so much questions, but two comments, some really interesting information you have, Jason. And the first comment is, as all of us as pedologists know, with what's going on in congressional and policy and all that about benchmarking carbon for carbon trading and all that, I think your 40 acres and the landscape that you showed has a great potential for a use of that kind of data as you continue to evolve it. So I say keep at it. That's really exciting information. The second comment I have is I like your camera and satellite and so on and so forth. And so one of the things I'm involved here in my conservation district, since I'm a retiree, don't have anything else to do. And one of the things, we have several projects, and one of those I have our staff, I'm a board member, so I have our staff go out and some of our projects, and they have to drive the roads like we've been doing for years and years and years in the spring and the fall and so on and so forth. And so my thought, if you're interested, we could put in for a NRCS CIG grant, bring you up here and demonstrate some innovative technology. So I'd like to visit with you about that. We don't need to do it today, but I'm just sharing that. I want to get ahead of Indiana and get this in Michigan, and because we're already doing it, as I said, by driving the roads. So I think this would be some really innovative technology, and obviously something NRCS I think would jump right on. And we have good relations, and I work closely with the state conservationists. So
great. I'd be happy to talk to you more about that, Jerry. Send me an email.
Okay.
That's the stage we're in right now, is how do we scale it up and get it out there into the hands of folks doing these transects.
Yeah. Sorry I couldn't. Thank you, and I look forward to visiting with you. And Matt, sorry I couldn't get back on my off my whatever mute.
No problems. Jason, there are a few questions that came into the chat here. First from Channer. He asked, I was curious if your lab had a chance to look at the correlation between GoPro car generated crop cover layers and the cropland data layer provided by the USDA.
Yep, so that's one of our benchmarks right now, is comparing to the CDL. I don't have the actual numbers on there right now, but the correlations are pretty solid. So we're kind of butting up against, for our previous crop predictions, we're butting up against the accuracy of CDL. So I think any mismatch in correlation is just due to either errors in our data or CDL, but I don't think we can figure out which one's which. So yeah, we're comparing it actively to CDL.
Thank you, Dr. Ackerman. That was also a very good talk. I really enjoyed it. I wanted to say that.
Oh, thank you.
There's a question, did you consider using a drone rather than driving around with the car?
Yeah, so we had talked about that. One of the challenges to using UAVs is maintaining line of sight. And we're trying to cover a whole watershed in a single day, right? So if you have a 2-mile line of sight, it's kind of hard to fly UAVs. And then also, I'm kind of trying to stay away from any legal issues of flying UAVs over farmers' fields. I don't think that's inherently illegal, but I don't necessarily want to have to fill out all the paperwork at Purdue to figure out how to get permission to fly a bunch of strangers' fields. So as long as we're staying on the road, we're kind of covered that way. But yeah, I think ultimately this is one tool that, maybe not drones specifically like quadcopters, but a low altitude fixed wing craft that could cover a whole watershed in an afternoon. It would be really easy for us to take that data and couple it with our existing point data set and build maybe even better classifiers than we're seeing with the Sentinel imagery, right? It's a 30-meter product we're using. We could get higher resolution products through low altitude fixed wing stuff. That would be great, I think.
Another question from the chat from Madi Al-Kasi. He's asking, what is the soil depth you used in simulating soil organic carbon in the Century model?
Yeah, so we use the upper 30 centimeters. We have data for the whole profiles, but we were just looking at the places that were most responsive to those changes. So I think, we see the rapid change in the upper 30 centimeters of the profile there. But certainly, I think that's one of the things as we're thinking about benchmarks moving forward, identifying what those reasonable depths to benchmark to is an important question, right? We certainly in our data, if we include just the 0 to 5 centimeter data, we see very much more rapid changes in those stocks versus if we use the whole soil profile. So I think there should be some healthy debate amongst all of us soil scientists about what the appropriate sampling depths there are for dynamic properties, soil health indicators, whatever we want to call them, to make sure that they're responsive to management, but also representing the full manageable portion of the soil profile.
I see Marshall McDaniel has his hand up. Would you care to share?
Hey, Jason, good to see you.
Hey, Marshall.
I enjoyed the talk. It's good to see what you've been up to in these past couple of years. It's cool. I got a question and maybe a comment too. I really enjoyed the benchmarking thing, and it's something I think about a lot. I was kind of interested in your thoughts on how you approach or why you called that the carbon max, though. I almost think of that as a minimum. I think it's a max loss. And I'm just curious why you and your collaborator decided to use that term rather than a minimum. I almost see that bottoming out and loss of carbon as a minimum, not the max.
Yeah, it's really just arbitrary. I was thinking about it as SOC at max T, I guess. But yeah, I think realistically, outside of scientific circles, I would never want to call that a max, right? It would be, if I was talking to policymakers, it would be a very different talk. But I think you're right. Yeah, it's a minimum. We do have soils that actually accumulated carbon in that Century model. So due to increased inputs of fertilizers and other ag chemicals, we see an increase in productivity that we think is related to smaller increase in carbon. That being said, I think I will admit the big flaw in that study is we're starting from our initial conditions are defined based off of Surgo, so the organic matter, organic carbon stocks in Surgo. What I would ultimately like to do is take these soils and then simulate them for 100 years and then change the management scenario to a different benchmark or different equilibrium state and then see how they respond that way. I think that'll be a more honest depiction of where these soils could start from. So it's something we're actively working on right now, is the sensitivity analysis of the initial conditions of those carbon stocks. Because I think that's a missing piece that we haven't really addressed yet.
Yeah, that would be really neat. The other thing, and I wonder if this, you kind of answered my follow-up question, but modeling the opposite, whether there's a carbon saturation, because that's, since.
Sorry, Marshall, I think we just lost your microphone.
Oh, hold on, Can you hear me again?
Yeah.
Okay, yeah, that always happens to me. I need to get a new webcam. Thanks for the patience. Yeah, you kind of answered my second question, but I was curious on the, if you could model the other direction rather than the vulnerable areas, but the areas where you could get the most gain in carbon, or where there'd be a carbon saturation level, right? There's been a lot of studies that say that there's, I don't know if I buy all of them, and I don't know if I buy this completely, but that there's a maximum level that you can achieve in the field. And I think of that as kind of the glass is half full aspect, right?
Mm-hmm. Yeah, I think ultimately that's where I want to go with this project, is thinking about, can we identify soils that might be but well below that saturation level, so we can say incentivize those particular farmers to maybe adopt carbon sequestration practices, or identify soils that are near saturation where it might be a waste of effort to try to do something like implement EQIP projects or EQIP grants for carbon sequestration. And I think there's ultimately some hopefully some real interest in the carbon marketplaces over the next year, and knowing what the potential for a farm is before enlisting it in a carbon marketplace might be a really critical aspect to pricing carbon or pricing credits.
Yeah, that'd be neat. Thanks, Jason.
Yeah, thanks, Marshall. It's good to talk to you.
Jason, we're just a couple minutes after 5, but there's one more question in the chat, if you don't mind.
Mm-hmm.
Michael Thompson asks, in the Paleostalf study, why was there a mismatch between the spectroscopic data and the lab data in the upper part of the profile than in the BT zone?
Yeah, so let me pull up my slide here real quick. But the short answer is, in the surface horizon, the A and the E horizons in those profiles, we're already so low in any sort of carbon or close your eyes, you're going to get seasick. Right here, we're already so low in any soil properties. So these soils, if you open up a pit, I wish I should have included a picture of this particular soil. It is fine sand, fine sandy loam, like bleached white. There's like nothing in it. There's hardly any clay content. There's hardly any carbon content. And the mismatch here is just due to the fact that we're basically hitting up the lower end of our detection limits for the instrument. So there's just hardly anything to predict. So we would expect to see that the data are more variable in those locations. I will say I kind of glossed over a lot of what's going on behind the scenes in our in situ work. As anyone who's colored soil knows, that as you add moisture to it, right, the color changes. The same thing's happening in the visible near infrared space. So one of the challenges with this tool is actually taking it and correcting for those moisture effects. And there's like a whole, chapters of my dissertation were written on correcting just those moisture effects. And that's probably has some impact there too, where we're seeing more or less moisture effects in the A and E horizons than we do see in the subsoils. So really don't have a great answer for you, other than sort of we're hitting up against the detection limits of the instrument, and we are just sort of kind of having to do a little bit extra heavy lifting to get rid of water content.
Well, thank you, Jason. It was a very interesting seminar. I think everybody would agree with that.